And I'll tell you why. When we get towards the end, I'm going to talk about lignocellulosic work that's being done at UFRJ. And they treat various celluloses like sugar cane. What do we use? We have corn. And bamboo is a lignocellulose. These bugs, they have an enzyme in their stomach that eats or that transforms the cellulose into sugar. Okay? That's kind of good. But we don't want it to happen to the bamboo building. Okay, here's some bamboo that's being treated. Really interesting. You can preserve this by smoking it. So instead of going out and smoking some weenies or some beef, you could smoke some bamboo. And it makes the rind unpalatable to the insects. You can put them in kilns. When it's cooked, the starch and nutrient content will be reduced and can reduce the susceptibility to cracking, which is a nice feature for structural applications. You can also soak this stuff in fresh water to remove starch and sugar. The bugs like the sugar. You know, all living creatures want sugar. You don't want to soak this stuff in salt water because bugs like salts too. And then you would coat it with borax or boric acid, which is ecologically benign. And there's also some lime slurries and rangoon oil. All the countries involved so far are not using insecticides. You need a long-term treatment, 50 years. Comparing wood to bamboo, there's a number of words here, but what's really interesting is if you take a tree, the hardest part of the tree is the core. And as you go from the core out to the outside where the bark is, the tree gets weaker and weaker. The material of the tree. Okay? Bamboo is the opposite. The weakest part is the center because it's air, except at the diaphragm. And you go out from the center, it gets harder and harder. Now, which is better for a structural application? That's a question you should put on the final exam. Hopefully it'll get 100% correct. Can we go back? This interesting picture taken by Professor Ghavami, it kind of shows, and I have a better one that's actual. This bamboo, this is the outside of the bamboo, what we call the thickness of the culm. It's made up of two things, fibers, which are very high in strength, and the matrix around the fibers, which is called the lignocellulose. This is what the bugs like to eat. That's also the piece that has sugar in it and salt. And so it's the waste from bamboo is just like the waste from sugar cane, the waste from corn, the waste from any biological plant. It's called biomass. And now there's people who want to take advantage of it. You don't just make ethanol from sugar itself, out of the sugar cane. You can make ethanol from the waste of sugar cane, the waste of bamboo, the waste of wood. Because there's cellulose in this waste. It's called biomass. So here's a chart. Professor Ghavami knows these numbers by heart because most of these numbers are averages because there's over 600 species of bamboo. 600. So you have a separate table for each species, and then of course you have different situations involving the species. Like whether the specimen is in the low part of the bamboo plant or the middle part or the top part. But look at it. These are the numbers I want to show you. I want you to look at it right down here. Look at the weight. And by the sorry, I've given these. These are in metric units. These are in English units. Pounds per cubic foot. How do we convert that to kilograms per cubic meter? Does anybody know? But this is wood, bamboo, steel. If I take the tensile strength and divide by the density, it's called the strength to weight ratio. 2.7 for wood, 7.5 for bamboo, 1 for steel. Why? Well, look at this. Steel is the strongest material we have, but it's also the heaviest and the most expensive. You can kind of, there's a sort of a relationship, linear relationship between cost and weight. Cost and weight. There, for example, if you ship these materials, you pay by the weight. So you could fill up a boat with bamboo and it wouldn't drop the water on it more than that far. Okay. Here's some testing that went on at Buki, I don't know what, 10 years ago, on the compressive strength of a piece of bamboo. I'm going to go through these real fast. These are some tests on the volume fraction of the fibers versus the position and the thickness. I don't know if you can see this, but this is blown up here. It kind of shows you where the fibers are, and then the lignocellulose matrix is around the fibers. Okay. Next. The people who investigate bamboo investigate strength, stiffness, and so forth properties here at what's called the diaphragm, or they call it the node. And then they also find the properties of the bamboo in between nodes. So there's a difference. The properties right at the node tend to be higher strength, higher stiffness. Okay. Recent developments in bamboo. I'm going to list a whole bunch of problems here in another couple of slides of why we're not using bamboo for engineered structures. One of them is building codes. You know, in the United States, with the exception of the two that you see here, we don't have a code that allows us to build a bamboo structure and tell the public, hey, we followed the code. In design with wood, there's many manuals showing different species of wood, different strength values, different requirements for treatment of the wood, because some wood we want to have underwater, some wood is above ground, some wood is in climates where it freezes 6 months out of the year, some wood is in climates that are extremely dry, others in climates that are extremely moist. And all these tables are design aids for a structural engineer to build with wood. We need that for bamboo. It doesn't exist. Yeah?
It would make sense.
So here's a couple of standards that do exist for bamboo. There's an ISO standard, and there's an ASTM standard, and now there's a standard for that material I mentioned to you called Lamboo. And who gets these things in the codes, by the way? Generally speaking, they're the ones who are the proponents of their own material. So they're usually not engineers who work at universities or engineers who work for the government. They're usually engineers who work for companies that produce this stuff because they have a financial interest in that. Yeah? The guys that got these standards for bamboo in the codes started the company called Lamboo Inc. They used to work in wood for 30 years. They were already on the committees, building code committees. So one of my recommendations is for some of the engineers here in Brazil, once you go out and get a job, to get on these committees. Okay. Now here's a pretty picture of a couple of things of Lamboo. As I said, Lamboo can be made to think of beams this wide and this deep, spanning, I don't know, 30, 40, 50 meters. And you can make arches like these, arches. Okay. Now here's examples of some old ways to connect bamboo. Old and current, actually. See, these guys are using bolts. take two bamboo poles, drill a hole through both of them, and put a bolt in there. Well, here's what happens to bamboo after you put a bolt in it.
That's a test we have done at Turkey.
Yeah.
With Pittsburgh.
Yeah, and so structures that are connected this way have been tested. But just keep in mind, these connections don't transfer bending moment. Yeah. For you civil engineers in here, you know what I'm talking about. If you want to make a structure strong, you don't need bending moments, but if you want to make a structure stiff, to follow deflection guidelines, to minimize deflections, you need to transfer moment between the column and the girder. There needs to be moment transfer. There's no moment transferred in a joint like that. So, bolts, danger, cords. What's wrong with this one? What's wrong with this for use in three-story bamboo structures that house people and large, heavy equipment? Well, nothing in the first year or two, but after 50 years, this stuff's not going to be here. It has almost no life cycle associated with it. Also, straps don't transfer moment either. They're just like bolts.
In order to control the serviceability.
That's right. Why do you want stiff structures? Because people don't like being in buildings that are swaying like this when they walk through the halls. It's just uncomfortable. Okay. So here's some connectors I've designed. I actually did these last summer. There's a student in here, Aresh, who worked with me when I started developing this concession. So there's some things that I decided that I wanted with my connectors. Number one, the key thing is that it had to accommodate a cylindrical geometry. It's not like wood. A tree is cylindrical, but what do? We send it to the sawmill, and the saws cut it into rectangular sections. Why? Because we want it to be rectangular, because our connectors are rectilinear. We are forcing nature to accommodate us. With bamboo, we have to think differently. This is why bamboo is so popular in the Eastern cultures. They accept bamboo the way it is, and they adapt to nature. Does everybody see the difference? If it's circular, you take it as it is. And you can't really cut bamboo. I mean, you can cut it in lengths, but you can't really do anything else with it, or you ruin the strength. So my connectors take cylindrical geometries. They do not involve bolts or screws or nails, but they do involve transfer bending moment. Those are the three key ideas. So these are made of very thin gauge steel, thin, so that they can be manufactured flat and then just rolled and welded. So there's a little bit of manufacturing that goes on with this. This is not carbon free. This would produce the carbon making these. And notice on these flanges, so a column would go in here, and two beams would come in here. Now, why are there these gaps? Because bamboo is not a uniform radius or uniform diameter like our wood is when we send it to the sawmill. So one end of a beam is a little bit different diameter than the other end of the beam. Well, we don't want to make a connector for every little tiny change in the diameter. So you have to have connectors that accommodate the change in radius at each end of a column or each end of a beam. And so these are gaps that allow us. I'm putting around these ends right here. I'm putting what we call a hose clamp, like you have in your car. Your car's got several of these hoses in it, and when it comes to a steel portion, you put a clamp around it, and you take a screwdriver and you just turn the screw, and it tightens this clamp down. Now, what's that called in Portuguese?
Braçadeira. Braçadeira.
Braçadeira
de mangueira.
Yeah, we need those. And so how is this thing supported? Through compression. The best force. compression around the bamboo, and the inside of these connectors is rough to enhance the friction. Does everybody see how this idea works? And this summer I'm going to test putting strain gauges here, 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 and here. And I'm putting strain gauges on the bamboo just as it goes in. Because I want to see if the strains, if the bending moment resisted by the bamboo itself is similar, maybe the same, as the bending moment transferred across the joint in the thin gauge steel. Does that make sense? So I'm going to load these things up. Let's go to the next slide. Well, here's my load head in the laboratory. This will produce several thousand pounds of load. And this is the way we're going to connect the poles. Like here's a bamboo pole. It's got a steel end in it. There's a bolt that's going to go through here. Next slide. Because on this test, which I call my elbow, this is an elbow, this is bamboo. I'm just going to put a pin here and a roller here and introduce a force there to create a bending moment here. And I'm going to measure the moment in the connector and the bamboo. And then on the other connector, I call this a T connector. You want to go back one? Okay. Two. This is the T, that's the elbow. This is that pin, this is a pin, this is a pin. This bamboo and this bamboo are going to have different loads. This load's going to be twice as large as this load to force bending across this joint, and so that this column will bend out. All right? I want the loads to be different, because I want a little bit of rotation to happen at that joint. Okay, so how much time we got left? Now I get to the real good stuff, fuzzy logic. I'm not sure where we actually started. Okay, remember the very first slide had this question, why aren't we using bamboo? And I've given you what I call the short answer, which is we don't have sufficient connectors, we don't have building codes. Primarily those two things that engineers can take care of. But the long answers involve a lot of different kinds of people, not just engineers. So here's some issues. Those are the first two. Growing and harvesting bamboo, that has to be enhanced. Distribution of bamboo, this is amazing. I asked these guys up in San Pedro do Serra and Pindorama, where do they take the bamboo that they grow on their land? Where do they sell their bamboo so that then it can be sold to engineers or whoever wants it? They said they sell it to a distributor. And I said, okay, how many of those are there? One distributor, and he's in Sao Paulo. Well, guess what's going to happen if there's only one distributor? Those economists out there, answer that question. Think about it. One distributor, what's he going to do?
Raise the price.
He's going to make a lot of money. So it turns out, if you want to buy bamboo from that guy, you pay twice what you pay for wood. Because there's a lot of wood distributors. There's competition. There's no competition with bamboo. That's a problem. Well, it's not a problem that can't be solved. Just put money out there and people will start becoming distributors. Coatings and treatments. I talked about this. This isn't really engineers so much as it is chemistry kinds of people, biologists. But somebody's working this problem. A lot of people are working this problem. They've got solutions. Skilled workers with training on how to do the building. As I said, if nobody knows how to make the building, to put it together, it's not going to go anywhere. So places like Pindorama need to be encouraged to do the training. Capital. None of this is going to happen unless there's money thrown in by investors. And I think this is a field that's going to grow exponentially. I really do. I wish I was younger so I could be more involved. This is going to explode, at least in my country. They're giving grants and benefits to anybody that develops new ideas in green construction or green anything. I call it Verde alguma coisa. Green something. Or green verde qualquer coisa. Money. And then finally, there needs to be a culture. You know, like in the United States, I wrote a grant about 3 years ago that was rejected. And there was only one reviewer, and he had one sentence. He says, "We can't fund this because we don't grow bamboo in the United States." That was the answer to my grant. That's ludicrous. Because we don't grow it. I wrote back to that guy and I said, "We don't grow mangoes here either, but we sure do import a lot of them." Banana, yeah. So, I don't know about Brazil. I think Brazil's got a little bit more, is more accepting of bamboo because it's everywhere. And people might be asking the question, what are we going to do with this stuff? It's everywhere. Here's some other things. Politics from other industries. Do any of you know the story of hemp? Professor Gavabi knows the story about hemp. Hemp was used, it creates cellulose, just like many things do. It was used to construct rope. Very strong rope. You know, you can make rope out of cloth, out of cotton, other kinds of cellulosic materials, but it's not as strong as hemp. And right about the time this happened, as Professor Gavabi knows, a guy named DuPont invented nylon. And he wanted his invention of nylon to sort of swamp this hemp market, because hemp is also used to manufacture clothes, ropes, many things. Well, hemp is a variant of marijuana. They come from the same, they're not the same species, but they're the same genera. Is that what it's called, genera?
Yes.
As marijuana. So what DuPont and several politicians in the United States did is they tied hemp to marijuana. They said hemp equals marijuana. And they were making marijuana illegal. This was 1930. They were making marijuana illegal, so they made hemp illegal.
45, 46.
And this other industry, which was called nylon, killed hemp. And hemp is just now coming back. People now know hemp is not marijuana. Hemp is useful. In fact, it's a cellulosic material that can produce ethanol in addition to ropes. Extensive marketing is required. There's going to be a lack of profits in the early stages. Why? Because there's no economies of scale. If you go in Rio, or my city, or any city in the world, you can find many, many concrete batch plants. Many concrete batch plants. They're everywhere. You can find many steel mills in all of the countries. Not as many as concrete batch plants, but a lot of steel mills. How many places are dealing with bamboo? There's no economies of scale yet. But there will be. If somebody starts putting in some capital. And at least in the United States, there's people who are wanting to do this. They need a plan. They need a plan. And Marco and I have been working on a plan. Okay. So here's where fuzzy logic comes from. Fuzzy logic is a routine that allows us to combine linguistic information or linguistic knowledge with numeric information. And, you know, the stuff I showed you about strengths and stiffnesses and these engineering properties, those are numeric. We don't need fuzzy with those. We need fuzzy with the concepts that would be necessary that deal with human experts. Like, how do you bring this product to market? There's no numbers. What's the best way to grow this stuff? How do you grow certain species? There's no numbers. How about treatment technology? How about technologies associated with the connectors? You know, many issues